Hello, welcome to another episode of Randy's Tech Tips. This episode we're going to be creating a counter using Golang. We're going to be using single-threaded, concurrent and parallel threaded counters. This is going to be a live coding example, so we're going to do it together. It's going to be quite long because there's quite a bit to cover and we're going to go through. Because it's live, there may be times that I just get stuck, and I'm going to try and leave those kinds of things in the video. If I get really stuck, then I will edit those sections out, come back as soon as I figured out something and try and explain it to you. And the reason for that is, one, just so that you see that there are places that everybody gets stuck in programming in. And then two, I don't really want to waste your time if I get stuck on something relatively simple. So without further ado, let's explain what we're going to be doing here. On the screen now, you can see that I have the very beginning of our program. All I've got is a main.go file, which is the main Go file. I'm using Go version 1.10.1, and I've made some notes in the application just to get us started, to try and help with the flow of the lesson. I will fess up now, I have created this before, however I've done it a few months back, so there's going to be stuff that I've forgotten and we're going to try and go through it again from scratch. Okay, so what are we counting here? So we need something to actually count, and what I've decided is that we're going to count slices of bytes that are going to be, they're going to contain letters. Now, I'm not going to put a particular limit on these slices, and as long as the computer is able to hold it in memory, then we're going to count that, and we're going to make the program so that it can be executed from the command line, and you can choose however many bytes you want to count. So I think that's probably a good place to start. Let's get a flag that will bring in an integer, and we'll use that integer to determine the length of our slices. Okay, so first thing we need to do is we create a globally scoped variables section here. Now, you don't have to put your variables for flags in global scope. I do because it just makes life a little bit easier for me right now. We're going to use the flag package. We're going to use the int, and we're going to L for length. I think let's start off with 1024 as our number, and we'll say here length of slice to be counted. Okie dokie then. So when we have flags, one of the very first things we need to do in our main program is we need to pass those flags. So let's do that. Flag dot pass. Not sure why my importer is not working, but import manually. I can spell. Of course, we actually need to assign it to something. So we'll say slice length equal to, there we go. Okay, so we've got our first thing. Now, I don't want to have to create these slices every time. I think what we should do next is create a function that takes the length and returns us a slice. So make slice, and it's going to take a length to be int return to us a slice of. Okay, so this note over here is going to be quite important to us. So we're going to be creating a slice of bytes, but we still want something to be able to actually print on the terminal so that when we run this thing, we can actually figure out whether or not this thing's actually working. So I'm going to be using the ASCII table, and the ASCII table basically has at position 65 the English letter A in capital, and then it goes all the way down to 90, and that is Z as a capital. So a little small. There we go, that should be big enough to read. So we can see over here, where are you? So 65 A, come all the way down to 90 Z. So when we create our slices, we want to create a number that is somewhere between 65 and 90. Now, unfortunately, Go doesn't really give us the functionality to pick a random number between 2 points. All they really do is give you the ability to pick a random number. It's not to mean that we can't do it, we just need to think of a different way of doing it. Now, we know that all of our numbers are going to have start at 65. So what we could do is we could say, Go, give me a number that is to a maximum of 26. And that way, or a maximum of 25, because 65 is going to be our first number. So that way we've always got a number that's in between 65 and 90, because we'll only ever be adding on the additional little bit to give us the randomness between 65 and 90. So let's do that now. So we go random add is equal to rand dot int in. I think this is the function. I want you to be something between 25. We'll also give our random generator a little bit of salt. So it's rand dot seed. Again, it hasn't imported anything yet, so I'm not quite sure if these are exactly the commands, but if I get it right, thumbs up. So it's going to be time dot Unix time dot now. I want now time, and then I want it to be converted to Unix and no, which will give us a int64 down to the nanosecond if my computers are able to support it, which I believe it can. If we save that, we'll get all of our things in, mainly because we haven't got the okay, and we'll see int n returns an integer and non-negative pseudo-random number between 0 and n. Okay, perfect. So we need to cycle in a for loop the length that's passed in number of times and add to a slice whatever our number is converted to a byte. Probably going to be easier to represent code here, so let's just go do that. So we're saying I want a for loop that starts at 0, 0, then needs to go I is the passed in length, which is L, and I. Okay, so add to. Now we need to make our slice first. Now slices normally, if you don't know how big they're going to be, you can just append to them. But we already know how big our slice is going to be. So to make things a bit quicker, we're going to create an empty slice that has enough slots available in it to add in every single one of these bytes along the way. So byte container, equal to make a slice of byte, and it's going to be L length. So now what we need to do is we add into the slice at I position the number that we come up with. This guy. Okay. Don't even use this. Quite literally say byte con. That this is going to be I. Don't forget we need to add 65 to it so that we get the letter. Time you go. We need to return now our byte container. Read. Return. How we complete. Correct, because I need to actually turn it into a byte. Like that, and then we don't use this guy anymore. Where would our life be without text editors? Okay, so I think that is our first function done. Okay, so create a slice of bytes. So I'm going to make a new note here. Single threaded count. I'm going to start with this one because it's going to be the basis for all of the others. Okay, so what do we need to do now? We need to create a counter that takes our newly made slice and then counts all the occurrences of a particular byte and then gives us back something that we could print to the terminal. So I think before we create the counter, let's rather create the terminal printer, because that way we know exactly what it is that our counter actually needs to return. So terminal printer, it's not going to return anything and it's going to have to take something. So I'm thinking that it needs to take data, which is going to be map of string, map of byte So in this case, what's going to happen is our counters are going to create a map where the key is the byte and the int is the occurrence of that byte. So we then need to cycle through each one of our keys. We need to turn it into a string, and then we need to put something like colon and then however many times it's occurred. So because it's a map, our range function gives us the key and the value. So we can just cycle through the data using the range, which is a built-in function. It gives us the key, the value, and now we can actually out. So now we just use bumped f print and then f actually because I'm formatting. Take a string, a colon, a space, and then a number. That is going to have to a string, then our value, but actually being able to test that right now, we're just going to have to hope that that works. So, trusty sip of coffee. And let's get our first counter. So counter, so did counter. So single threaded counter, going to give us some data. We're going to make this function in a minute, and then we're going to print terminal printer. Hold it. Terminal printer is going to take data. Just to make our lives a little bit easier, we're going to time these, and we're going to see how long each different method takes in order to complete its task. So print ln starting thread counter. So I've got a capital T there. I think we should get the date stamp on there. Dot now. Actually, rather than doing that, put it at the end, because that way we can actually do a time. So one, make a timer. So time dot now. Then we make our next timer as soon as our single threaded counter has finished its work, and that way we can figure out how long it took. So 2 is time dot since. It takes a duration or a starting time, which is our T1. So now we can say from print threaded counter is finished. Took this is going to give it to us in nanoseconds. So we may need to divide this a little bit, but I think for now, let's just see what it gives us. Can't honestly remember. We should be able to see, once we see the number, we should be able to tell straight away. If it's an absolutely massive number, then it's probably in nanoseconds. But yeah, we'll figure that out when we get there. For now, let's focus on our single-threaded counter. So counters. So it's a function. It's going to need to take something to be satisfied. And in this case, it's going to be, I think, a white slice. It will return a map of type string means over here we need to create our slice. So let's create our slice. So slice is equal to make slice equal to pointer to our slice length. That is when, because we told it that single-threaded counter would return a map string when in fact it should actually return a map of byte in. Okay, so our single-threaded counter needs to go through our bytes over here. So we're going to call it count me. So write it out as 4. So doing this as soon as I typed it. So again, I'm going to have to try and remember the way this comes around. So a range on a slice will give you the index that you're currently on plus the value at that index. Now, we don't particularly care for the index. We only really care for the value that is inside of that point. So we need to make a map before, because we need to start it. So turn data map byte Okay, so now we'll say that return data of e plus equals return data. That's even better. Thank you, Visual Studio. There we go. So what have we done here? So we use the range to go over the loop or over our array, and that will give us our index and then also our value. We then take the value and we put it inside of the map. And the reason we can use a plus plus is because Go will instantiate the map with its 0 values. And that way, when you use plus plus, it'll start at 0, and then you get 1, and then 2, and then 3, and then 4, and so on and so on. And eventually we'll just return our table, which then comes up to the top here. It will give us our single thread counter, which will go to our data, and should give us a terminal print. Now, I think we may actually have something to run here. So let's give it a go. Hey, look at that. Now, it looks like we forgot to add in a new line. Why everything is washed up. That is on our terminal printer. Here we go. Now, you'll notice that our letters are jumbled. And the reason that they're jumbled is because maps in Go are inherently random. And they're actually coded to be random so that you as a developer do not rely on maps being a sorted set of some kind. If you want something to be sorted, then you should be using a map random. That's just it. So we know what values we're looking for here because we've got a very limited set of values that can be the keys for our map. So to make our letters come in the right order, we need to change our terminal printer to rather use a counter or a for loop inside of it that goes from 0 through to 25, and then we add 65 to that, and then we call that byte out of the table, and that way we'll get A, B, C, D, and so on and so forth. So let's do that, because else when we're trying to compare values, it's going to get very confusing because we need to start grappling with our eyeballs to try and find letters, and that's just ridiculous. So let's fix it. So we said that we needed to do a for loop, and our for loop needs to have a key, and the key I'm just going to call it K, starts at 0, and it needs to be less than or equal, no, it's less than 26, and needs to, put K there. K will just get incremented off every loop, and we need to, instead of this thing over here, just be K now. This value actually going to be the value that's in the data. So now we'll say something. Data then we'll go byte ID. What's byte ID? We're going to make that right now. So byte ID equal to whatever K is plus 65 turned into a byte. So comment that out for a second. Let's run it again and see. Oh dear, I appear to have broken it. So we're definitely getting our numbers. It's because we need to use byte ID here also. There we go. Now I suspect that I'm out by 1 here. Or something we got is out by 1. Scroll up, 4, look, Z. Doesn't even look like we got a Z in there. Nope. Okay, so we are out by 1 on one of our counters. I know that's cheating, but that's kind of one way to fix it. I think make slice. Okay. But that looks a bit better. Now we've got a continuous counter. It counts however many bytes in there, and it also puts our output in order. Now, although the table's pretty, and it's nice to be able to see that the numbers are there, when we start running this thing over and over and over, what we really care about is going to be this timer over here. So let's make another flag, and we're going to call this one verbose, which you'll see over here. We've got this flag which I said we needed, which was verbose, and that verbose flag is going to dictate whether or not we get the table for the letters. So you need to come right up to the top again, create a new variable called verbose flag, and we're going to use the flag package again. This time it's going to be a bool. Verbose going to be false by default. Explanation. So grab that and we'll use it down here in our terminal printer. Now we this guy because we don't need it anymore. Say if pointer to verbose flag there we go. So our verbose flag, it's already a bool. It's false by default. So unless you actually use the verbose flag, you're not going to see anything. So let's see that in action. There we go. As you can see, we're just now starting to get the timers rather than the table, which, in all honesty, is good for me. Okay. So the next one that we have is, so we've done that one. We've got the formatting in human readable. So get rid of that. I've created something that could the occurrence, apparently misspelled that, and store it in that thing. So we've done that. Okay, so the next one is a concurrent counter on the slice. Oh. So what are we trying to do there? So for this example, what I had in mind is to create something that would count the occurrences of the bytes in our slice, but using the same slice. So if you'd imagine you had a deck of cards on the table that had, I don't know, like 10,000 cards in it, and there were 4 or 5 of you around the table, and each one of you was just like going over that stack, and you're all counting a set of cards till you get to the bottom, and then add it all up together. So, is it faster to count as a single counter, one person, or is it faster to count as 10 people counting off of the same stack? So that's what we're going to go look for now. So this one's going to be a little bit more complicated, and yeah, let's get on with it. So we're just going to scoop up what we've got before, and I'm going to put it underneath this comment. Create the times again. And we're going to edit the texture. Current created. Call it starting concurrent counter. Current finished. Took however many seconds. Don't need a space there, because print ln will add a space in between each one of the things that you pass into it. Okay. So our data again, and this time on current counter. Okay. So it's a function again. Oh, and what happened there? So it's a function called concurrent counter. It has a thing passed to it called count me, which is a byte slice, and like the other one, it returns a map of byte and okay. So this one can't work the same as the last one. In this case, what we're going to have to do is make use of Goroutines inside of Go. Now, if you don't know Go at all, think of Goroutine as really cheap threads. What will happen is that when you tell Go to fire off a Goroutine, it will take your code, it will send it off to another thread, then it will move on to the next step. That second thread that you spawn will go through all of the function call or the code that you basically told it to execute, and then it will just die, because essentially it's finished doing its job, so it will just exit out. It allows you to work concurrently or in parallel, depending on how you code stuff. And you'll see that in our counters here, which is actually the main takeaway from this, is the idea of concurrency and parallelism, but then also when is it a good time to use it. So for our counters, we need to create our people around the table, and we only need a certain amount of them. So we're going to use the runtime package, and we're going to use the number of CPUs. So I have 8 of them, this computer, I believe, because it's a quad core with hyperthreading. It'll give me 8 threads. So I should be able to handle 8 Goroutines. So essentially 8 people around the table to count the cards. So we're going to call that workers. Runtime.num. That's what the function is. Yep. Num CPU returns a number of logical processor units usable by the current process. Now, important thing to note here. I think it was in Go version like 1.6 or something. They changed the behavior that a application would have enough threads to run on each one of the CPUs. So previously to that, they would only have a single thread and all of the Goroutines would run on that single thread. But now they will have as many threads available to them. Okay, so that's how many workers we want. So now we're going to spawn our workers, and we're just going to get them to count off of this thing. And you'll see we'll grow this thing out. So just bear with me for a little bit, and we'll grow it out. So the number of workers, we want I to be equal to 0. The workers. So this for loop is literally just going to fire off workers. Work. And work will take an I. So we'll leave it at that for now. So ID is just going to be I. In fact, why don't we just call this ID, because that'll make it a little bit easier to understand when I read it in a few months' time. Okay, so that's our work. Now, how do we get our data from inside of a Goroutine to our main thread? Now, Goroutines, they don't share any memory at all. So the only way that you can get them to communicate is by having them talk to each other through some form of communication. So Go has a thing called channels, and we're going to use those channels here. We're going to use the channel to pass it data, and then we're going to use another channel to have the Goroutine send the data back to us once it's complete. Okay, so we need some channels. Let's make some channels. So we need the workflow channel, and that channel is going to contain bytes. So it's a pan that holds bytes, has maximum capacity of 10. So what does all of that mean? So panels are kind of like a table. If you're going to pass something to someone, you pick up your box of information and you come to the table and you put down your box of information, and then you walk off. And you pick up another box of information, you come back and you put down the box, and you expect that the person who's going to take the information will come to the other side of the table and they will pick up the box and take the box away. So you expect that every time you come to this table that there's going to be space for you to put something on the table. But let's say, for instance, that your job is just to pick up the box and put it down onto the table, but the other person's job is to pick up the box, sort whatever's in the box, and then take it to somewhere else. Now, that sorting operation may take a bit longer, which means that at some stage, when you pick up your box and bring it to the table, the table's going to be full. At that point, you have to sit there, wait for some space to open up on the table. That's what this 10 over here is. We're saying that there's 10 units of space on this table, and once it's full, you've got to wait. Now, it's a good way to synchronize code or to rate limit code, and don't let things just explode in growth, because you could end up in a situation where you're just using way too much memory because one thing's just backing up and the other thing's just running really, really slowly. Rather just have thing that's filling up the queue just slow down a little bit or just stop for a while, because there's no point if there's something on the other side that's not picking it up. Panels can also have no units of space. And in that case, all you're really doing is you're making a place to meet, and one thing has to hand over to another thing because there's nowhere to put the box down, so you have to give the box to the other person. And that's really good if you really need synchronization. You're waiting, your sorting operation has to finish before you can take another one. You can't just back them up for the whole day. Okay, so in our case, we're looking just to basically rate limit our work, and we're going to put 10 things into the queue, and then when there's 10 things in the queue, we'll just hold up for a second, or however long it takes to get a new space, and then once it's all finished, we'll close that channel. And we'll get to closing channels, get to writing it, and we'll explain what it does there. So we need another channel, and that is so that the worker can send data back to us as well, because we're giving it bytes, but we want those tables back as well. And those tables need to come over a channel. So essentially, we're going to have a channel which is a worker complete, and it's going to be channel that holds a map which is, like what we said before, a byte and an int. Will hold as many units as there are workers. So we're not going to deal with the actual counting yet. We're going to deal with what happens, how we get the data into there. And there is a reason for that, and it's to make sure that we understand what our flow is, so that when we create our worker, we know exactly what it is that we want the worker to do. So we're going to feed the worker some work via a channel. So let's do that. So we're going to take the stuff out of the byte slice, and we're going to give it there. So thing equal to range over our count me, because we don't know what it is. It's just the thing, it's just a byte. So for every thing, we're going to send that thing into the workflow. So workflow, the arrow mechanism is how we send down a channel, and we get the same thing. Okay, so once we're done sending all of the data, we then need to close that channel. So why do we close that channel? We close the channel to notify the workers that all of the work is complete. If they can't receive anything more, they can't count anything more, so then they will exit. So now do workflow, close it, like so. So once we've closed our channel, we then expect the workers to come back to us and say, hey, I've completed, I've counted everything, there's your map. So we can use the for loop over a range on a channel. And we expect that every worker needs to give us something. So we will count for however many times the worker, however many workers there are. Equal to workers okay, and then what do we need to do instead of here? So we need to take every map that we get, we need to iterate over all of the values, and then we need to add those values to a map of our own. So the key word there was map of our own. So we need to create our own one. So complete equal to, so make map white so we need to now select on our channel. So we're going to say data places. So data is equal to whatever we get on our channel, which is, what is our channel called? It's worker complete data. Okay. We'll also need a default, which is when our, we don't even need a default because we know that we're going to get this many. Okay, so now we're saying need another for loop over here, and then we go key value range data. So this is basically the same as our terminal printer, where we're just cycling over it, over our data, and now we're just going to add it in. Say complete data key plus equal whatever our value is. So because they're always numbers, that we're always just going to add on however many got from that. That is that. So we should, at the end of this, close our completed workers data channel, just to save resources. Okay, got a whole bunch of things that it doesn't like yet, but we'll fix those in a minute. Okay, so one of the things that we need to do is we need to slow down our main function here, so that when we I'm going to pause because I'm about to run out of battery. Okay, so life happened. It's a couple of hours later. Battery is charging. I haven't actually touched the program, so we'll just jump back into where we were. So it looks like I've got a lot of red lines here, and it looks like that is because, here we go. So that is supposed to be a semicolon, and then the same thing over there because we copied it. And Pania, can you data is tab. That is because what we want is that one. Okay, so we've got our flow here, but we've got one more thing to do before we can actually get into what our workers themselves are doing, and that comes back down to what I said about how Goroutines work. So when I said that Goroutines will just kick off something, the thing on the side will just execute, and then our thread will just carry on going. There's at no point are we actually going to wait for that other Goroutine to finish. So we need a way to actually wait and know when those other Goroutines are all finished executing. Because if we were to not wait, what would end up happening is that this queue over here would just sit here empty. So what we really want to do is we're going to create something called a wait group. That wait group will wait for a number to come down to 0, and then once it hits 0, it will just carry on from there. And it holds the numbers, well, let's just type it. It's going to be easier if we describe it as we type it. How about that? So we create a wait group here. It's in the sync package. This once. It's a pointer to a wait group. Okay, and then what we do is that creates a empty wait group, and now what we need to do is just start adding counters to the wait group. And the idea is that we add 1 to the wait group every single time we start a worker, and when the worker is complete, the worker will call waitGroup.done. That'll remove 1. So we're just adding the number of workers into the wait group, and they will just say when it's done. So waitGroup.add, and we add a number. So you could add more than one. I haven't really seen the time where you would do anything like that. And then inside our worker over here, we would call waitGroup.done. But the important part is over here. So here we do waitGroup dot. And why do we do that? So this is a good place to stop working and wait for all of the workers to finish, because we've signaled to the workers that we are done dishing out work, so they can now signal to us that they are done. And at that point, we expect that our queue will be full of results, and then we can just cycle through the results. Okay, so I think that our flow is done. Now we need to work on how the workers are going to work. So we can do this in 2 ways. We can either use an anonymous function and we'll put everything inside of here, or we could make a function and pass it in all of the things that it needs. For simplicity, I'm going to create a function. I'm going to pass in the things that it needs, just to make the code a little bit easier to read. So function is a concurrent worker, a little c. And what does it need? Well, we said that it needs 3 things now. It needs both the channels, but it also needs a wait group. So the first channel, we said, is just a channel that does bytes. So workflow, workflow, cham. It is a chan that holds bytes. Okay, then we had a completed data channel, and it is a chan that holds a map of byte to int, and we also have a wait group, which is a pointer to a sync.wait group. So we can see. Okay, so the code for this is actually pretty easy because our workflow is now really easy to understand. Our workflow is we receive on the workflow channel, and when we're done receiving on the workflow channel, we send all of our data back. So how do we know when a channel is closed? So first thing, we need an infinite for loop. The reason we need an infinite for loop is because we don't know when work is going to be finished, so we can't actually say in our for loop what the guidelines are for when it should end or when it should stop. So we have to have something inside of it that will stop it. The next thing we use is a thing called a select, and that gives us the ability to have multiple cases. So we can also do something like this. So byte value, okay, that will receive on our go. So what's okay about that? So channels will give us two things. It will give us the value, and if we call on a channel that is closed, we will get an error. And not necessarily an error, it's more just like it's all broken. So we can do something like this. If not okay, return, no, not return, send. Okay. Make ourselves a worker map. Going to be map byte and int. Add down the channel. Okay, but if it is okay, that means that we got a value, and then we need to actually put that value to use. So brain had a freeze moment there. Okay, and then just before we're done, we also need to tell the wait group that we're done. We got a bit of red over here. That's because we need this thing. Oh yes, we also said that. Why did we need the ID? We don't need the ID. Grab that worker and replace that function. Okay, so now we need to just pass in all of the things that we need to give to it. So it's first thing is the workflow channel. Next thing is worker completed data channel. And last thing is the wait group. guess the question is now, does it work? Okay, what happened here? It says a wait group is reused for previous wait as returned. The pointer that's a pointer, that's a pointer. Going on line N. Curious. I am not sure what is going on here. Okay, this is one of those moments where I'm going to have to pause it. Okay, it took me a little bit to figure it out, but I eventually figured it out, and I'm going to show you how we did that. So you'll see in the terminal now, get rid of one of them. I've got some print statements just to show me what's going on, and those are these things over here. So I use this to tell me when the channel was closed, so I could see when the worker was exiting, but I also used this print statement to tell me that the worker was actually coming online. So I can see that the workers themselves were coming online. However, I noticed that over here in this run, I noticed that although I had 8 workers come online, I had a lot more returns happening. So what that told me is that this section of the loop is being run over and over and over again, till eventually the sync package just blew up. And that's because we forgot to return. Nice and easy. But it did take quite a while to figure out because it's a very, very easy thing to miss. Something else then broke straight after that, and that is this thing over here, where it says that all of the Goroutines are asleep. And the reason for that was over here, I had this looking like that. But that meant that we were out by 1. Because we would run the loop from 0 all the way through to 8. But that's actually 9 instances. There would only ever be 8 things of data here, and the case statement will block waiting for data to be returned out of that channel. Remember the analogy that we used earlier where we said that a channel is just a table with space on it. If the person sorting the files arrives back at the table expecting there to be a box to be sorted, but there's nothing there, they will just stay there waiting for the person to deliver the box. But if there was only ever 8 workers and all the work's done, then the box will never arrive. So we end up with a deadlock. Go is kind enough to actually tell us about that. So let's get rid of these print statements because we just don't need them anymore. We also don't need our ID anymore. We'll get rid of it there, and we'll get rid of it where I passed it in over here. But that is pretty much everything that went on. I was also making use of our flag just to try and get our counters working. So we'll introduce that now and we'll see what happens. So we'll use our flag and we'll say, I want you to count 5,000 bytes. Oh no, it's broken again. That's because I left that equals in again. Here we go. Okay, so here's an interesting output that we should look at quickly. So the single-threaded counter took 300 microseconds, or roughly 300 microseconds to complete. But the concurrent counter took 983 microseconds. Now, that's a lot more. That's nearly 3 times more. Oh, it's more than 3 times more to count the same amount. So it turns out that in this instance, using more CPUs is actually slower than using a single CPU. We can make that number a bit bigger so that we can actually see how long it takes. There it is in seconds. And then this is going to be vastly longer. There we go. So it just doesn't work out. And this is kind of the reason why I wanted to make this video, especially working with counters, is to show that although concurrent programming is good, it has its limits and it should be used when it's needed, not just for the sake of using it. In this instance, our single-threaded counter is vastly better than our concurrent counter. But there is still a use for this. So if we change the counting scenario slightly, and we rather say that instead of counting how many bytes are in a single array, what if I said that there was 10 arrays and I needed to count all of them? Well, in that case, we're probably going to end up with a much better, much better performance by using parallel processing, which is not the same as concurrent, because concurrent is the idea of doing things at the same time, where parallel is doing multiple things or multiple different things at the same time. So in order to demonstrate this, we need to make 2 new counters, and we're going to quickly zip through them. The first one is like our single-threaded counter, but it's also going to cycle through our slice of slices, and eventually at the end of it, it'll give us everything. So that one's pretty easy to make. So what we're going to do is we're going to make that one first. So how far are we in here? So in our comments. So we need to make a slice of slices first. Okay, so how do we do that? Well, we can already make a slice. So now all we need to do is make 10 of them. But we need to store them in something. So we're going to make a new variable, which is going to be slice of slices. And that's going to be slice of a slice of bytes. I'm going to have 10 indexes in it. So now we need to go for I equal to 0. I is then 10. I plus. Now I specifically want I to be 0 in this case because slices start at a 0 index. So slice of slices at index I equal to make slice of size L. But L length is pointer. Okay, so now we've got a slice of slices. So now we're going to do a, we'll call this one a serial counter. The reason we're calling it a serial counter is because it's literally just going to count slice after slice after slice after slice and give us a map back with all of that data. So starting serial slicer, serial slicer, serial counter is finished. Call this one serial counter. Serial counter takes a slice of slices. Okay, that looks good to me. Down to the bottom here, and we'll make a new function. So a serial counter, it takes a SOS, which is slice of slices, and it's going to be one of those. And it returns a map of byte and int. Probably worth pointing out at this time that if your length is way too big, then your map is just not going to work because it won't be able to carry the int sizing. So this one's actually pretty easy because we can use our function that we've already written, so our single threaded counter, because it actually does exactly what we want, except we just need to wrap it in a for loop to feed it in the slices and then compact all of the maps that it gives back to us. So that is going to be S, and then we go for index and the value. It's going to be S of SOS, slice of slices, that, and that's going to give us back some data. Need our own table, so serial counter map to a new instance of a map bytes and int. Okay, so as soon as we get our data back, we need to go through our data and value range over data. Serial counter E plus equals the value. And then once all of that is done, just have to return this. Put range over there. Okay, so that one was pretty easy. Let's give it a decently sized number. Let's say 50,000, and let's see if it works. Okay, well that's not too bad. So to count 50,000 for our serial counter took 29 milliseconds roughly. So our next counter, and this will be our final counter, is a counter where we make use of the channels and the Goroutines again, but instead of counting the same thing, what we're going to do is we're going to farm out the arrays, or sorry, the slices out to the Goroutines, and then just consume all of the ones that are, or we'll compact them as the Goroutines finish them. So we need to come up to the top here, and we make a new parallel counter. I'll bring this. So same again. It's parallel counter. Parallel counter. Parallel counter finished. Parallel counter, and it also takes a slice of slices. Okay, so new function, parallel counter. It takes SOS, which is a slice of slices which have bytes. It returns a map, exactly the same as all the others. Byte and int. And now we've got to do a thing. Okay, so this one, what do we need to do? We need to create some Goroutines. They need to have channels to send the data back and forth. We need a wait group again. So let's make all of those things. So we need a workflow channel, which is going to be, so this time it's a chan that holds a byte slice, and it's length of 10. Then we need a work complete. Okay, same as that one. It's going to be pretty much the same again. So a channel that holds one of those, and it will be however many workers we have. And over here, exactly the same thing that we had over there. Pretty much that with that. So we'll grab that, put it there. This is length workers. Okay, and we also need a wait group. I think dot group pointer to a wait group. Okay, and now we need to farm out our work. So the index, just need the sorry, we need to spawn the workers. I is equal to 0. I is less than workers. Okay, then go worker get to make that in a second. We'll call it one a para worker. Okay, we need to add to the wait group. Then we need to feed the work. So every slice inside of our slice of slices, we need to send that down and the workflow channel. workflow channel gets S, and when that's finally done, we will close that channel. So you see that the workflow here is pretty much the same as the last one we did. It's only how the work gets handled that is really going to be the key difference here. And then we wait. So once all of the Goroutines are finished, then we can come and merge all of our data. So, yeah, so for all data equal to range on a channel, we'll just consume everything in the channel. And then say, we need to make our own table. So return data to a new map for the value in range of data, turn data, get in there, here we go, plus equal to value. Finally, return the return data. Now we're done in this loop. We'll close because we are good citizens. Okay, so the parallel worker, it is going to take, well, let's quickly create that function. So what does it need? It needs a workflow channel, workflow chat, which is going to be a chat that holds slice of bytes, and needs a return channel, which is a channel that holds a map and it also needs a wait group. Pointer to a dot. Okay, so let us nearly there. So for this one, we just need to consume off of our panel. So it's going to be the same thing again. So select on our channel, we have a case statement, and it's going to be work, okay. We have to check to see when the channel is closed. Workflow channel. If not okay, now the channel's closed. We're not going to get this wrong now. We're going to do return right now. We're going to do the work group, and we need our own table. So worker table is equal to, so tired of typing this out. One of those. And we need to send it down the return chan. So return chan, then that thing. So that's if the channel's closed, because then we know that all the work is done. So what do we do if when we do get work? So because we're getting a slice of bytes, we can use our very first function again, our single-threaded counter. So that's exactly what we're going to do. Our single-threaded counter is going to take our work and it's going to give us some data back. And then we're quite literally going to use that loop to feed the data in. Not that one. Oh, should have just typed it out. That one. And it's going to go on our return table, sorry, our worker table rather than our return. I think that's probably it. We just need to feed in the values now. So we said it needs the workflow value first. Then it needs return channel. Then it needs the weight group. So there's no red or anything. And I think all the logic's there. Run it. Where have I messed up? It says that all the Goroutines are dead. That's over. Yeah. That's a good point. So although I said that we will just consume on a channel, there's nothing to tell this for loop when the channel's actually closed. So we can't actually use this way of doing things. So let's quickly edit that. That needs to be a for loop. I'm going to write it up an infinite for loop. And it needs to have a select statement on it. And we also need to do a check to see if the channel is closed with the OK statement. So return data, OK. Nope, that's also not going to work. We need to do it for the amount of workers that we have. There we go. That's what we need. Okay. Paste. And the return data, don't need the OK because we know that this channel is always going to be open. Going to be a selecting or a collection off of this channel. That, place data with that. Leave it as data because we've got something called data, return data already. Get rid of that. This complaining about. Unexpected power worker. Yep, it's because we've got an extra one of those. There we go. Okay, so now we are going through our loop for as many times as there are workers, and each time we select something off of our channel. We merge our channel together. So we merge all of our return data from our channel together. We close the channel and then we return. Give it another go. Yeah, there we go. So I just wanted to quickly re-record the end because I noticed that my head was actually right where all the numbers were. So let's quickly take a look at these numbers again. So over here, we can see that we've got our single threaded counter. Remember, our parallel counter and our serial counter are counting 10 instances of the same that our single threaded counter is doing, and it's taking just under 3 milliseconds, but our concurrent counter is taking just under 9.5 milliseconds to count the same thing as the single threaded counter. Now the serial counter is taking 30 milliseconds, but it's doing 10 times the amount as a single threaded counter. Now you see that 2.9 is pretty much 10 times that, so it's pretty consistent there. However, to count the same amount as our serial counter, but in parallel this time, it actually takes 7.63, which is a massive saving in time. To be completely honest, I'm not sure why the concurrent counter takes a lot longer. If somebody does know, feel free to comment. I'm sure I'll learn, and many other people will learn a lot from that. But I have a suspicion that it's because of all of the memory allocations that go on when you're shoveling data in and out of channels, and also just reading from a byte over a channel. It just seems like, reading bytes from a slice over a channel just seems like a very inefficient way to get something done anyway. But doing it in parallel, where you've got 10, and in this case I'll have 8 of them counting at the same time, maximizes the CPUs that I've got available to me. So it's a very, 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 very good way of programming when it's needed. And that, I think, is what we should really take away from this, is although it's cool to make counters and write some code and everything, the fact that we have to use the right type of programming complete the task that we're trying to over here. So that's the end of the lesson. If you enjoyed what you learned, subscribe. If you have something to say or want to say thanks or want to point something out, feel free to comment below. If you liked it, thumbs up. And that's all. Cheers!